Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 9, and today we are going to learn a very interesting topic, that is Mohr circle. So, this is basically a graphical way to find normal and shear component of traction on arbitrary planes. But the only restriction is that the plane normal has to be perpendicular to one of the principal axes. All right. So, let us see what we mean by this. So, that means if you write down your stress matrix and the normal vector in a convenient coordinate system, such that let us say the third coordinate axis is along the principal axis, then the normal directions are such that n 3 is equal to 0, because we are only looking for planes which are perpendicular to the third principal axis. Okay. So, in such a coordinate system, can you guess how will the stress matrix look like? So, in the coordinate system in which the third coordinate axis is the principal axis, but first and second need not be principal axis. So, in such a coordinate system, how will the stress matrix look like? If you write down the stress matrix, the third column is formed by the traction on the third plane, but that is the principal plane. So, it will not have any shear component, right, it only has the normal component, which means the third column would be such that the last entry is non-zero, but the other two are 0, is not it, because it is a principal plane. And then from the symmetry we would know that these two are also 0, while the other components could be non-zero. So, this is the kind of stress matrix that we are looking for, because the third axis is the principal axis. And what about the direction? The normal direction. So, that is a sigma matrix, whereas the normal direction n, that becomes cross 0, right, because again it is we are only looking for planes which are perpendicular to the third axis. So, those planes have normal of this form. All right. So, we want to find out the normal and shear component of traction on these planes, but graphically. Okay. So, to do that we will have to derive some formula which you would apply graphically finally. Okay. So, let me draw the cuboid here. For such a coordinate system, the cuboid, so that is the cuboid, and suppose that this third one is the principal axis. So, that is the principal axis, and these two are not the principal axis. So, say this is E1, this is E2 and this is E3, which is a principal axis. So, on third one we only have normal component of traction acting. So, if we write down all the traction components, so we have sigma 1, let us call it sigma xx, because that is how people do it in many books also. So, along 1 it is x, along 2 it is y, and along 3 it is z. Okay. So, that this becomes sigma xx, and then it has tau y x, right, on the x plane, but in the y direction. So, it has got tau y x, and on the 2 plane we have tau x y, and we know that they are same, and it also has got sigma y y, sigma y y. Okay. And on the third one it is just sigma z z, which is actually lambda 3. So, on the third one it is sigma z z, which is equal to lambda 3, right. And then there are many other faces also, if you allow me to draw them. So, on this face we have the normal component sigma xx, and we have the shear component tau yx, similarly you have the bottom face. Let us not make it complicated. All right. For such cases there is another simpler way to draw the state of stress, because we know that on the third direction there is no shear component. So, people also draw just a square, instead of cube they draw a square. And then the sides, the edges of this square are actually denoting the planes. Okay. So, this is this edge, the vertical edge actually goes inside the paper and forms the E1 plane. Okay. So, this is your E1 plane, okay. And then we have E2 plane, the top edge actually corresponds to E2 plane. Okay. And the face that you see here, the face of the paper, that is the E3 plane. So, on this face we only have sigma z z, right. So, we could put a circle with a dot to denote that we have got sigma z z here, but on the edges on E1 plane we have sigma 1 1 and tau 2 1, right, or sigma x x and tau y x, which is equal to tau x y. So, I will just write it as tau x y, okay. Whereas, on the E2 plane we have tau x y and sigma y y. On the negative E1 plane we have sigma x x and tau x y. On negative E2 plane we have sigma y y and tau x y. Okay. So, you have to understand that we have mixed up tau x y and tau y x are same. So, I am writing everywhere tau x y. Okay. So, that is the state of stress. You see the cube has reduced to a square. So, cube reduced to a square. And now, our goal is to get the normal and shear component of traction on planes which are such that the plane normal is perpendicular to E3, is not it? So, we are basically looking for planes something like this. The blue line is basically when goes into the paper you get the plane, okay, and the normal to the plane, that is the n, the plane normal, all right. You see the normal n is perpendicular to E3, is not it? And the blue line goes into the paper to form your plane, the n plane. Okay. Suppose that the normal makes an angle alpha from the E1 axis. Okay. So, we have the E1 plane rotate by alpha degree about E3 axis to get your n plane. Okay. So, n plane by definition is then rotate E1 plane by angle alpha about E3 axis. So, what will be the column corresponding to n in this coordinate system? It is n1, n2, 0, and n1 is cos alpha, n2 is sin alpha, is not it? So, n1 is cos alpha, n2 is sin alpha, and n3 is 0. So, that is the n, and I want to find out the sigma and tau on this plane. So, my goal is to get sigma and tau. So, that is your sigma and this is tau, and look at the direction of tau. So, we have to go anti-clockwise from the normal direction to find out the direction of tau. See, we could have chosen the tau to be either going upward or downward, right, but the convention here is we go anti-clockwise from the normal direction 90 degree to get the direction of tau. Okay. So, we want to get tau in that particular direction, all right. So, what will be sigma? So, sigma we then use the formula, right, which is simply sigma matrix into n, and then you dot it with n So, plug in all the values. Sigma matrix is sigma x x, tau x y, zero zero, sigma z z, and then you multiply this with cos alpha, sin alpha, 0, and then the whole thing you again dot with cos alpha, sin alpha and 0. Okay. And so, you work it out and finally, you will see that this becomes sigma x x cos square alpha plus 2 tau x y sin alpha cos alpha plus sigma y y sin square alpha. Okay. So, that is the formula for the sigma. And what about tau? See how to get tau? Find out the total traction on this plane and then take its component in the direction of tau, the direction that we have chosen here. Okay. So, what is n perpendicular in this case? See, the n perpendicular has got its E1 component negative and E2 component is positive. So, that is the n perpendicular we have chosen, the direction for tau. So, n perpendicular which has to be perpendicular to the n vector. So, what does that become? The E1 component is negative. So, it becomes minus sin alpha and E2 component is positive, this becomes cos alpha and the third one is 0. And you can check if you use this n perpendicular, then n perpendicular dot with n becomes 0. All right. So, with this n perpendicular, what will be tau? So, your tau as defined in that picture is simply sigma matrix multiplied by the n vector. This gives you total traction and you dot this in the n perpendicular direction. For the sigma you dot with n, for tau you dot with n perpendicular, all right. And you put your values for n perpendicular, for n and for sigma, and finally, you will get this equal to minus sigma x x cos alpha sin alpha minus tau x y sin square alpha plus tau x y cos square alpha plus sigma y y cos alpha sin alpha. Okay. So, you work it out, put all the values and this is what you will get. Now, we can play with these expressions to make it more nice. Let us see how to do that. For example, suppose I want to do for sigma the normal component, this expression. So, I am going to rewrite it as sigma equal to sigma x x plus sigma y y by 2. Okay. So, I added something, so I have to subtract that also, plus sigma x x into cos square alpha minus 1/2, because sigma x x by 2 was added and I subtract that, plus sigma y y into sin square alpha minus 1/2, right, very simple, plus 2 times tau x y sin alpha cos alpha, is not it? You will see why I am doing it like this. Let us just follow the steps. So, this implies sigma is sigma x x plus sigma y y by 2. Now comes the thing, this cos square alpha minus half, use trigonometry, and what is it? 2 cos square alpha minus 1 is cos 2 alpha. So, this is nothing but cos 2 alpha by 2. Okay. So, we get this as sigma x x cos 2 alpha by 2. Similarly, sin square alpha minus half, that is actually minus of cos 2 alpha by 2. Look at the trigonometry, you will see it. So, this is minus sigma y y cos 2 alpha by 2, okay. And then the last one, 2 times sin alpha cos alpha is sin 2 alpha. So, this is simply tau x y into sin 2 alpha, all right. So, finally, this is sigma x x plus sigma y y by 2 plus sigma x x minus sigma y y divided by 2 into cos 2 alpha plus tau x y times sin 2 alpha. Okay. That is just some algebra trigonometry, you get to this expression. Likewise, you can work with tau also, the expression for the shear component tau. See, you have to look at the expression, you have minus sigma x x cos alpha sin alpha. So, cos alpha sin alpha is what? Sin 2 alpha by 2, is not it? Similarly, sigma y y cos alpha sin alpha, that sin 2 alpha by 2. For tau x y, you have cos square alpha minus sin square alpha, that is simply cos 2 alpha, all right. So, finally, you have tau equal to minus of sigma x x minus sigma y y by 2 times sin 2 alpha plus tau x y cos 2 alpha. Okay. Now, you can see for the expression of sigma and tau that right before us, you have cos 2 alpha sin 2 alpha present there, and the coefficients of cos 2 alpha and sin 2 alpha are flipped for sigma and tau, is not it. So, you can now define something called scalar r is equal to square root of sigma x x minus sigma y y by 2 whole square plus tau x y whole square. Okay. So, I define an r in this way. If you do that, you can think of a right triangle. Where the hypotenuse is this r, the vertical line is tau x y, whereas the horizontal line is then sigma x x minus sigma y y by 2, all right. Suppose this angle is 2 phi, then what can you say about cos 2 phi? So, cos 2 phi is then sigma x x minus sigma y y by 2 r, is not it? And what about sin 2 phi? That is tau x y divided by r, right. So, let us substitute this in our formula for sigma and tau, all right. So, we have everything here. So, in the formula for sigma, we have sigma equal to sigma x x plus sigma y y by 2 plus take a common of r. So, when you take r as common, you have to divide by r also, and then you see, can we write it as cos 2 phi cos 2 alpha plus sin 2 phi sin 2 alpha, right. You took a r common and then it becomes this. Now, I guess you can see why we use those variables. And for the tau, similarly, when you take r as common, then what do we get? Then the first term is sigma x x minus sigma y by 2 r, and what is that? Cos 2 phi, right. So, we get minus cos 2 phi sin 2 alpha, and from the second one we have tau x y by r, that sin 2 phi sin 2 alpha, is not it? Now, you have to again use slight trigonometry. So, in the expression for sigma, you have cos A cos B plus sin A sin B. What is that? That is cos of A minus B. In the second expression, you have sin A cos B minus sin B cos A, which is sin of A minus B, is not it, where A is equal to 2 phi and B is equal to 2 alpha. So, if you use that trigonometry, so finally, you have a very simple expression for sigma. So, sigma becomes sigma x x plus sigma y y by 2 plus r times cos of 2 phi minus 2 alpha, whereas tau is then r times sin of 2 phi minus 2 alpha. Now, can you see the formula became really simple now? So, let us box this. Okay. See, this is the formula to get sigma and tau on any plane with angle alpha, right. You remember the plane n was rotated by an angle alpha from E1 axis. So, alpha, you have to put that alpha in this formula. For phi, how do you get phi? So, you have the formula for cos 2 phi sin 2 phi, then what is tan of 2 phi? Tan of 2 phi is then simply tau x y twice of it divided by sigma x x minus sigma y y. So, you see you start with a sigma matrix of that given form, and then you have to find out the sigma and tau on a plane which is rotated by alpha. So, with this sigma matrix you first find out phi, the angle phi, using this formula that tan 2 phi is equal to 2 times tau x y over sigma x x minus sigma y y. Once you get your phi, you can also get the radius r, right. For radius r, you have to use this formula, square root of sigma x x minus sigma y y by 2 whole square plus tau x y whole square. You see r and phi, they are all in terms of the stress components, and then plug in your alpha here, right. So, you simply get sigma and tau on any arbitrary plane with angle alpha, just that the plane has to be such that the normal is perpendicular to E3, otherwise alpha could be anything. So, this is mathematical formula, is not it. So, you just have to remember this formula, and then let us see, can we somehow graphically show what does this formula mean. Okay. Can you see what does sigma and tau represent? If I find out sigma and tau for every alpha and then plot it on sigma tau plane. Okay. Think of a plane whose x axis is sigma and y axis is tau, all right. On this plane, for every alpha you start putting a dot for sigma tau. Now, can you see what is that formula going to give you? So, that is going to give you a circle. What is the center of the circle? The center is such that on the sigma axis, the center is at sigma x x plus sigma y y by 2, and the y axis of the center is simply 0, right. So, the first step is basically to draw the circle. So, you start putting sigma x x somewhere. So, let us say your sigma x x is here, then your sigma y y, and the center is average of the two. So, that is the center, sigma x x plus sigma y y by 2, with x axis this value and y coordinate 0. So, it lies on the sigma axis. And what is the radius of that circle? That is square root formula. Okay. So, you also find out where is tau x y, let us say it is somewhere here, tau x y. So, this point corresponds to sigma tau for E1 plane. Okay. Join it with sigma x x, and you will see that this line is actually the radius. Why? Because the circle has to pass through the point corresponding to E1 plane, because the circle is the locus of all sigma tau. So, the sigma tau corresponding to E1 plane also has to lie on the circle, right. So, therefore, once you have the center of the circle and you have a point on the circle, join those 2 points, you get the radius, right. Can you see, is it really matching with our formula? Then yes, it is matching. See, the vertical line is tau x y, and what is the horizontal line? What is this value? Sigma x x minus sigma y y by 2, is not it? and this is what that triangle was. Remember, the vertical line was tau x y, horizontal line was sigma x x minus sigma y y by 2, and so the hypotenuse is that radius r. So, once we have the center and a point for E1 plane, get your radius, draw the circle. All right. So, that is the circle. Can you guess where is the angle 2 phi? So, 2 phi was the angle of that triangle, is not it? So, this is that angle 2 phi. Now, to find out sigma and tau on any plane with angle alpha, what should you do? Look at the formula and the circle. From the formula, for a plane alpha, the angle has to be 2 phi minus 2 alpha. See, the argument of cos and psi is 2 phi minus 2 alpha. So, the argument reduces by 2 alpha. So, what should you do on the circle then? Can you guess what should you do on the circle? The center is at sigma x x plus sigma y y by 2. So, the radial line should make an angle 2 phi minus 2 alpha from x axis. All right. So, this is then point corresponding to alpha. And this angle is your 2 alpha. So, that the angle between the radial line and the x axis sigma axis is 2 phi minus 2 alpha, is not it? We have to reduce the angle by 2 alpha, and then this point, the dot point that you see, the green dot. So, that is the alpha plane. So, sigma and tau corresponding to the green dot is actually the sigma and tau on alpha plane. So, do you see what we have to do? So, step is very simple. So, the first step is number 1, draw the center of circle at sigma x x plus sigma y y by 2 comma 0. Okay. Number 2, draw the sigma comma tau for E1 plane, which would be at sigma x x comma tau x y. So, once we have these 2 points, the line joining the above 2 points forms the radius of the circle. Okay. So, with that radius, draw your circle then. So, with center and radius known, draw your circle. So, once we have the circle, now to find out sigma tau, to find sigma tau for a plane with angle alpha, rotate the radial line joining sigma tau for E1 plane by 2 alpha, but clockwise. See, if the angle alpha is positive, and how is alpha positive? Look at the initial picture. So, we rotate by alpha about E3 axis. So, about E3 axis you rotate by alpha counterclockwise. So, alpha positive means we rotate counterclockwise. Okay. So, if in the actual plane, if the actual plane is found by rotating in the counterclockwise direction, then in the Mohr circle you have to go clockwise by 2 alpha. If the actual plane is by alpha counterclockwise, in the Mohr circle you go twice of that angle and in the opposite direction clockwise. If the actual plane is alpha clockwise, then in the Mohr circle you go 2 alpha counterclockwise, because you see in the formula it was 2 phi minus 2 alpha, it comes with a minus sign. So, clockwise here becomes counterclockwise in the Mohr circle, and counterclockwise here becomes clockwise in the Mohr circle. So, that is all you have to do. All right. Let us see what all information can be extracted from the Mohr circle. Let me redraw the Mohr circle. So, let us redraw the Mohr circle. So, we have sigma x x, we have sigma y y, then we get a center at the midpoint of the two. So, that is a center. Then draw the point for E1 plane. So, sigma x x and tau x y, that is the E1 plane. Join center and E1 point, that is the radius. So, with center and radius known, draw the circle. Okay. So, draw the circle. And then this angle becomes 2 phi. So, we are on sigma and tau plane. So, what all information can we extract? See, first of all, so this is your E1. To get to E2 plane, what should you do? What will be alpha for E2 plane? So, by how much you have to rotate to get to E2 plane? So, alpha is 90 degree counterclockwise, right? You go 90 degree in the anti-clockwise direction and you reach the normal of E2 plane. So, in the Mohr circle, to find out sigma and tau on E2 plane, what should we do? we should go 180 degree, but clockwise, right. So, let us go 180 degree clockwise, and where are we then? We will be exactly on the diametrically opposite point, right, because it is 180 degree. So, you go 180 degree diametrically opposite and you reach here. And what is then sigma and tau at this point? You can see sigma is sigma y y, which should have been, and what will be tau? It will be same as tau x y, is not it? You see, due to similarity of the triangle involved here. So, if you draw these lines, so because it is 180 degree, the two triangles are similar, and therefore, the height is tau x y here, but you get negative tau x y. Can you see why it is negative tau x y, whereas in the actual picture we have tau x y positive? Why it is becoming negative? Any idea? So, the question is, why is tau negative on E2 plane? So, I will write here for E2 plane, we rotate by 180 degree clockwise, and then the question comes, why is tau negative on E2 plane? So, you have to go and look at your convention. Let us go up and see which direction is the direction for tau, n perpendicular. Do you see that? We move anti-clockwise from n by 90 degree to get n perpendicular. Do the same thing for E2 plane. For E2 plane, the normal is along E2. So, this formula, the Mohr circle, will give you tau in which direction? So, from E2 you rotate 90 degree anti-clockwise. What direction do you get? It is minus E1, is not it? So, Mohr circle is giving you tau on E2 plane, but in the minus E1 direction, whereas this tau x y is the shear component in the plus E1 direction. Therefore, Mohr circle is giving you minus tau x y, all right. So, you can remember that. Why is tau negative? Because n perpendicular for E2 plane is along minus E1 direction, all right. So, that is one take home message. So, what other things can we extract from this Mohr circle? See, what is the maximum value of sigma from this circle? Any idea? So, this Mohr circle is the locus of sigma tau on all the planes, right, for all alphas. So, among all these points, where is the maximum? This is maximum, is not it? That is the maximum value of sigma. So, I will say this is max sigma, whereas this is minimum sigma, right. Where is the maximum shear stress, shear component of traction? at the top and bottom of the circle, right. So, this point is max tau, or let us say max magnitude of tau, and this point is also max magnitude of tau. Can you see, are they matching with the formulas that we had derived? So, what is lambda 1 then in this case? What will be lambda 1? The maximum sigma. Suppose that the principal stress components are lambda 1, lambda 2, lambda 3, and arrange them in a fashion such that lambda 1 is greater than lambda 2, greater than lambda 3. Okay. So, lambda 1 greater than lambda 2, greater than lambda 3. So, here what is then lambda 1? So, you know the center, you go by radius along the x axis and you reach lambda 1, right. You go by minus radius, you reach lambda 2, is not it. So, lambda 1 is basically the center, which is sigma x x plus sigma y y by 2 plus radius, right. And what will be then lambda 2 minus radius, sigma x x plus sigma y y by 2 minus radius. So, if somebody tells you what are the principal stress components, what will you do? Sigma x x, sigma y y will be known, radius you know from that square root formula. So, put them here, you get your principal stress components, right. In terms of principal stress components, where is the center? Center is sigma x x plus sigma y y by 2. If you do lambda 1 plus lambda 2 by 2, that is also the center, right. So, this point, the center of circle is also equal to lambda 1 plus lambda 2 by 2. All right. Here is the catch now. What can you say about the radius in terms of lambda 1, lambda 2? What is radius? So, you have the formulas for lambda 1, lambda 2. What is radius in terms of lambda 1, lambda 2? Subtract those two formula and divide by 2, right, to get your radius. So, the radius r is also equal to lambda 1 minus lambda 2 by 2, is not it. Now, do you think it is matching with what we have derived in the last class? In the last class, what was the maximum value of shear component of traction? Do you recall? Lambda 1 minus lambda 2 by 2, is not it. And from Mohr circle, you see what is that value? That is equal to radius of the circle. The max tau is at the radius of the circle. So, it is matching, right, which is equal to lambda 1 minus lambda 2 by 2. What is the sigma corresponding to max tau? The point where you have maximum tau, what is the value of sigma? The value corresponding to center of the circle, which is lambda 1 plus lambda 2 by 2. Is not that what we had derived, right? The plane on which we have maximum shear traction, we also have normal component of traction, and that was equal to lambda 1 plus lambda 2 by 2, and that is what we see here also, right. So, for the maximum point, we could also say that this is same as lambda 1 plus lambda 2 by 2 comma lambda 1 minus lambda 2 by 2, is not it? So, we have confirmed our previous results from this Mohr circle. So, let us just stop here and we will do more about Mohr circle in the next class. Okay? You will see things get very easy when we work with Mohr circle. Okay? Thank you.